Hey y'all, in this lesson, we're going to talk about Venn diagrams, subsets, and we're going to use the real number system to explore those things. Before we get into using a Venn diagram to show how the subsets of the real number system relate to each other, we're going to talk about a little bit of terminology first. A universal set is the set that contains all elements under consideration. So if we're specifically talking about the real number system, then the universal set would be real numbers. And then within the real numbers, we have subsets. So that's what we're going to be looking at today in a Venn diagram. A Venn diagram is just a picture representation of how sets relate to each other. And it's usually using some shapes like rectangles and circles, and the rectangle represents the universal set, which in this case is the real number system, and then or the real numbers. And then inside that rectangle are circles or ovals or whatever shape you want to use that sometimes overlap. And when they overlap, that means that they have something in common. So I have an example down here of kind of a skeleton of a Venn diagram. So I've got basically we're going to fill this in with the real numbers, but I want to talk about the real numbers before we start building this Venn diagram. So I'm going to go back up here and I've got these sets listed out, and we're going to just kind of describe what types of numbers are in these sets. So I'm not going to necessarily give you the mathematical definition. I'm just going to kind of give you some examples as to what goes in there. So natural numbers, you can see I've got them all listed out. These are all subsets of the real numbers. I have real down here. Natural numbers are the numbers that you think of when you naturally, get it, start counting. So the natural numbers are numbers from 1, 2, 3, 4, 5, and so on, all the way to infinity. But it starts at 1, which is where you naturally start counting. Whole numbers include all the natural numbers, but one new number appears. And it's a number that occurs before 1. It kind of looks like an O. Hopefully you guessed it, 0. 0, 1, 2, 3, 4, 5 goes to infinity. So I'm stopping at 5, but it goes all the way into infinity, which is forever. But we use this ... we use this ellipses to show that it continues in the same pattern. So whole numbers are the natural numbers plus 0. So we could say natural numbers plus 0. One thing I forgot to mention is we usually use symbols for these sets. So for natural numbers, it's an N with kind of a double back there. For whole numbers, it's a W with a little, I'm terrible at drawing it, but you get the idea. It's kind of got that extra little line on it. Now, integers, if we can picture a number line, on the number line, we know that whole numbers make up one side of the number line, but there is another side of the number line. The number line can go into another side, the left-hand side of it, which is the negative numbers. So integers include the negative side of that number line. Like if you spend too much and maybe your bank account goes into the negative. So -3, -2, -1, 0, 1, 2, 3. All of these are examples of integers. Again, we're still in the counting type numbers, whole numbers. So no fractions or decimals yet, but now we've started including negatives. So we're building out these sets. We've started with the natural numbers, which start at 1, and then now we've added 0, and now we've added the left-hand side of that number line, which is negative numbers. So our integers include the whole numbers and the natural numbers, but we're building out the set. So now we've got negative. Now I mentioned that these are just counting numbers. They don't include fractions or decimals, which means that now we need to account for those numbers that we use. We use fractions and decimals when we spend money or bake cookies or cake or whatever. So anything like that, that's called a rational number. A rational number is a fraction or a decimal. So technically speaking, any number that can be written as a fraction, and a fraction is a ratio of integers, the second of which cannot be 0. So it's written as A over B, where B cannot be 0. That's the definition of it. So any number that can be converted to a fraction is considered rational. So 0.5 would be 5/10, which is a half, or 0.3 repeated is 1/3, or 2. 2 can be written as a fraction as 2 over 1 or 4 over 2. So it's kind of tricky. You kind of have to look for it a little bit, but anything that can be converted to a fraction is a rational number. These are going to be fractions, obviously, and then decimals that have a pattern or repeat. So when you're looking for those rational numbers in disguise, any of the decimals that have a pattern like 1 2 1 2 1 2 1 2 or repeating or terminating, sorry. So terminating means it stops. So 0.5, that's it, or 0.1875, and that's it. Those types of decimals can be written as a fraction, which is a rational number. And then irrational, hopefully my accent is not getting that confused when I say irrational and irrational. It kind of sounds the same, but they're not the same. They're actually totally opposite. So there's rational and there's irrational. You cannot be both. You're one or the other. And by you, I mean numbers. Talking about numbers, I give numbers personalities. I don't know. Irrational is any number that cannot be written as a fraction. These are going to be your really yucky decimals. That's not a math term. That's a me term. Yucky decimals. So decimals that have no pattern. Decimals with no pattern or no termination. No, it doesn't terminate. So actually, I have some really easy examples here. Sorry, I'm running out of room, but pi is irrational because if you look at the decimal for pi, it never ends and there's not really like a noticeable pattern going on. So if you type pi in your calculator, it stops because your calculator's memory is full. So it stops there. But if you actually like Google pi, the digits of pi, it goes on and on and on and on and on forever and ever and ever and ever and ever. So that's considered irrational. Or square root 2, or square root of any prime number, square root 3, square root 5, square root 7, anything that's going to just turn out kind of yucky. Let me show you what that looks like in the calculator. Square root 2. Look at that decimal there, 1.414213,562, and then my calculator stops there. So there's not really any pattern. It's just kind of irrational. one might say. It's just kind of yucky. So that's an irrational number. Any number like that is irrational. And those two, rational and irrational, those two sets do not overlap. It's one or the other. So that's going to kind of help us build our Venn diagram. And then your real numbers are all the numbers above. That's going to be considered our universal set. So when I go down here and I build out this Venn diagram, I've kind of got it set up. The universal set is the real numbers. You know what I forgot to do? I forgot to give you the symbols up here. Real numbers, it's an R with a double back. Irrational, I believe they use a Q for that. Nope, I'm wrong. That's rational. Sorry about that. Irrational, I think sometimes they use an I with a double. There's several different ways they do that. I usually use an I. Integers are a Z with a double thing. The Q and the Z come from the Latin origin of the words, I believe. But if you're using symbols, those are the symbols for that. Let's go back down here. So we have our real numbers. That's the universal set. That's all the numbers that we're talking about, the numbers under consideration. There are imaginary numbers, but that's not what we're talking about. We're talking about real numbers. And inside the real numbers, we have two categories. We have rational and irrational. Rational and irrational. It's not necessarily, I've got this, it kind of makes it look like the set of irrational numbers is smaller because of the way I have it set up. That's not necessarily what I'm saying here. It's just how I drew it. Because inside the rational numbers, I have subsets. The rational numbers are made up of integers. So I'm going to draw a circle for integers. And the integers are made up of whole numbers. And the whole numbers are made up of natural numbers. Ah, that looks ugly. This is where those symbols would come in handy. Make this a little smaller. Natural. There we go. So we have our real numbers is a universal set. Inside the real numbers, we have rational and irrational. It's one or the other. But within the rational numbers, we have these other subsets. So that brings me down to some terminology down here. The complement of a set is basically everything that's not in the set you're talking about. So the complement of rational would be irrational. They complete the real numbers. Let me think. Trying to figure out how to word that. So all elements not in a set being discussed that are in the universal set. I was trying to figure out how to be, you want to be very specific in mathematics. So I was trying to figure out how to be specific there. We denote complement. There's two different ways I've seen this. If we have a set A, the complement, you can do a little apostrophe, or you can do a little lowercase c. That looks like an O, lowercase c. Either one of those is fine. So in this example here, we have the universal set A, B, C, D, E, F, G, H, and we have the set M, lots of letters here, A, C, F, G. Find the complement of M. So the complement of M, the set that would complete M, would be everything not in M. So the complement of M. Now M contains A, C, F, G. So the complement of M would be B, D, E, and H. And if I were to add the two sets, M and its complement, it would make up the universal set. Isn't that neat? So you kind of think of a complement like not like, oh, wow, you're really pretty, but more like what completes the set. So for example, in real life, if you are with a significant other, some significant others are opposites. So like me and my husband, I am brown hair, green eyes, yellowish skin, olive skin, I should say. My husband is blonde hair, blue eyes. He's my total opposite. He's tall, I'm short. Our personalities are total opposites, so we complement each other well. He completes me. So that's kind of how you can think of complement when you're studying. And then I have already talked about subsets, but just to kind of give you a more defined definition, a refined definition of this, A is a subset of B if every element of A lives in B. So if I can find every element of A inside the set of B, then A is a subset of B. So kind of, you can view it kind of like, it's not necessarily smaller, but in my mind, I think of it's like a smaller set. So it can be equal to, but we'll talk about that in a second. Getting off track. So M is a subset of U because every element of M lives in U. Also, the complement of M is a subset of U because every element in the complement of M lives in U. And then we're going to practice that. The symbol for subset, I didn't have it here, but you can see it right here. The symbol for subset is kind of this sideways U with a line under it. And then not a subset is just a slash through that. So subset, regular U with a line, and then not a subset, slash it through. I love doing that little slash. It's fun. So we're going to practice these, try them, pause it, try it, come back and check your work. Should end up with one of each here. In part A, 1, 2, 3, 4 is a subset of 1, 2, 3, 4, 8 because every element in the first set lives in the second set. And then in part B, so close, but no go. So this is not a subset because of the 3. The 3 disqualifies it. 3 does not live in the second set, so it is not a subset. And then I want to go up here. Sorry for the traveling. My notes are a little out of order here. I do want to talk about this up here. This was on the previous page when I was talking about the real number system, but I want to talk about this before I go into the next thing. 2 sets are equal when they contain the exact same elements. So they have to be equal in number and equal in elements. For example, if we had 2 sets, the first set maybe was 2, 4, 6, and then the second set was like that set maybe in disguise. For example, 4 minus 2, 2 plus 2, 3 plus 3 look a little different, but when you simplify them, they're actually the exact same sets. Or you could write this as the original set maybe in different order. Either way, but they are equal. They're the same. They have the exact same elements. And then I also want to talk about finite versus infinite. So finite is easily countable. For example, I'll just do it down here. If I had a set 2, 4, 6, 8, or if I had a set of students in a classroom, those things are countable. And then infinite means that it's a set that extends into infinity, goes into infinity. And technically we can't count it. We can't count infinity. Now there is a concept of countable infinity, and that relates back to one-to-one correspondence with the natural numbers, but we are not going to cover that in this video. That would be a whole separate video, but for the sake of determining if something is finite or infinite, we're just going to think in our minds, can I count it? Can I not count it? And that's where we'll go there. So for example, infinite might be x such that x is an odd number. We're going to consider this infinite because it is infinite because we can't count the set of odd numbers. It goes on into infinity. We could start now and count forever, and we would be counting until we went into a greater place. So we call that infinite. Now let's go back down here. Sorry for the crazy ride. There we go. And let's talk about set equality now that we know about finite, infinite, all that good stuff. Set equality using subsets. Now we know what a subset is, so let's use subsets to define set equality. You have set equality only when if A is a subset of B and B is a subset of A, then the two sets are equal. Now let's use that to define a proper subset. Proper subset happens when A is a subset of B, but A does not equal B. We call that a proper subset. And we denote this with just a sideways U. So down here we can see we've already talked about a regular subset that has the little line under it. And then we have a proper subset that does not have a line under it, and that is referring to this definition. So knowing that, I want you to try these two examples here. Pause it, try it, come back. Should have one of each. We have A is a proper subset because the first set is a subset of the second, but they are not equal. And then in part B, it is just a subset, not proper subset, because it is a subset and they're equal. That's all I have for this lesson. I hope you enjoyed it. If you have any questions, please let me know. I'd be happy to help. See you in the next one.